Hi, well, I'm Stephen Eshiba, and I'm going to talk to you a little bit about modeling an isothermal atmosphere around the planet. So here's my depiction of planet Earth. Here it is. Got some radius r. Now I've drawn the atmosphere around it as if it were, pretty separated, but of course we know that it's really just a very thin atmosphere that's right around the planet. I've just done it this way so I can highlight some of the processes that are going on. So one process is that we have a shortwave coming in from the sun. That's I1, which is given by this expression here. It's the solar constant, 1367 watts per meter squared. Take away the part that got reflected, the albedo, times pi r squared, because pi r squared is the target area that the Earth presents. And so that's a short wave incoming, and we're just going to assume in this model that all the short wave passes right through the atmosphere. None of it gets absorbed on the way in. How about I2? I2 is the long wave emitted by the planet. And, well, we know what that term looks like too. It's sigma times t to the fourth. T is the temperature of the planet's surface, times 4 pi r squared, because that's the surface area of the Earth. Now, we have a few more processes that are going on that we need to take into account. One of them is the fraction of I2 that gets absorbed by the atmosphere. So this long wave is trying to get out to space. The photons that are in the atmospheric window, sure, though they can get out, but the ones that are not are going to get absorbed. So we have to have an expression for I3. And, well, I'm going to just have to introduce a parameter. It's the absorptivity of the atmosphere. That's the fraction of outgoing long wave that gets absorbed. So this part should be straightforward enough. It's A times I2, right? I3 is the fraction of I2 that gets absorbed, which is governed by the absorptivity. And how about I4? Well, I4 is the part of I2 that didn't get absorbed by the atmosphere, so that's got to be 1 minus A times I2, okay? Good. Now, the atmosphere not only absorbs light, but as we know, it also emits light because it's a gray body emitter. That means it has some emissivity, smaller than 1. And according to Kirchhoff, the emissivity is just equal to the absorptivity, so we can say that. And I've drawn it here so that to indicate that we've got radiance coming down, coming back out. Since it's all one temperature in the atmosphere, that radiance down and will equal the radiance up. So so we just need to decide on I5. Well, a gray body emitter, we know that's epsilon times T to the fourth, but which temperature? Well, that's got to be the temperature of the atmosphere, so I'll write it down this way. Temperature of the atmosphere. And times sigma. We need a sigma times T to the fourth. And, of course, we need a 4 pi r squared because that's the surface area of the planet. Remember that the atmosphere is really just as big as the planet. And, of course, I6, as we've said, that's just equal to I5. And, okay, now, the last bit of this then is what are the radiative balance conditions? And physically what we're going to say is I want the Earth to be in radiative balance, so it's neither heating up nor cooling down. And I want the atmosphere to be in radiative balance, so it's neither heating up nor cooling down. So to do this, all we really have to do is look at the arrows. So coming into the surface of the Earth, I see I1. Okay, so I1 is there. And what else is coming down? Well, I5 is coming down, so plus I5. And now that's offset by the long wave coming off right there, I2, so I'm going to say minus I2. And that, to be in radiative balance, has to equal 0. How about the radiative balance condition for the atmosphere? Well, once again, we do the same thing. We just look at the arrows. Let's see, I see going into the atmosphere is I3. Okay, so I have to say I3 is going in. Now, we don't have to worry about I4 because I4 is just the part that got transmitted through. And so we don't have to worry about that part. But these really are leaving the atmosphere. This is with the energy that the atmosphere is emitting. So I have to say minus I5 and minus I6. And if that's equal to 0, that means the atmosphere is also in radiative balance. Now, we have two equations, two radiative balance equations. We have two unknowns, that is to say we don't know the temperature that the planet is going to settle down to, and we don't know what the temperature of the atmosphere is going to settle down to. But two equations, two unknowns, that's enough to solve those, and we have a few methods to do that. One of them is by hand, but the one that you'll be doing is to be solving those on a computer. Okay.